Welcome to the CoSpaceRobot family. CoSpaceRobot is an official platform for both RoboCup and RoboCup Asia-Pacific CoSpace Challenge. CoSpace Autonomous Driving Platform is powered by CoSpaceRobot Studio. Apart from the CoSpace programming interface, it provides interface in Scratch, Python, and C. Please visit our website to find out more.
If you have decent experience with programming or have completed CoSpace Auto Driving First Steps and you are above 12 years old, the Auto Driving U19 is designed for you. In this session, we will give you a step-by-step guidance to the CoSpace Auto Driving. We hope it will help you to have a better understanding in the CoSpace Auto Driving Advanced level and to take part in the CoSpace Autonomous Driving Challenge U19 category.
Line following is probably the most common application in robotics. It is widely used in industries and even hospitals. If a robot can think, the thought process of a line following robot will be very similar to that of a human being. And that can be simplified into 3 actions: sense, plan, and act. CoSpaceRobot will give you a unique first-hand programming experience in such applications. Let's take a look at the CoSpace Virtual Robot. It is equipped with one color sensor to sense the floor RGB color, which is the short form for red, green, and blue. One gyro sensor to sense the robot's orientation. One ultrasonic sensor to sense the front obstacles, and 6 infrared IR sensors for line tracking. What is the logic behind the robot's thinking process when it tracks a black line? The 6 IR sensors mounted on the robot are like 6 eyes of the robot. When the first left IR sensor, we call it L1, senses the black line, the robot needs to move forward. When the first right IR sensor, we call it R1, senses the black line, the robot also needs to move forward. When L2 senses the black line, the robot needs to turn left slightly. When R2 senses the black line, the robot needs to turn right slightly. When L3 senses the black line, the robot needs to turn left rapidly. When R3 senses the black line, the robot needs to turn right rapidly. This process repeats forever in a loop, and this will ensure that the robot tracks the black line. Let's code a line tracking program in CoSpaceRobot.
For optimal performance, your PC laptop should meet the minimum configuration. Let's watch a video guide on installation.
Hello, good job. We are almost there. Let's click on the Experience button to see if our computer is compatible with this software. While we are at it, let's also check and see the version of our software. It's always good to have the latest version. Awesome. It seems that our computer is compatible and our software is up to date. And now it's time to activate our software. So there are 3 options: Learn, Compete, and Experience. So for this example, we're going to use first steps. All right, we're going to click on Workshop Pack 1. The activation window has just popped out, so please make sure you're connected to the internet and input your account number as well as your serial code, which is also your license number. So these will be given to you via email, so please make sure to check your email. And also please make sure when you put in your serial code, there are no spaces in the front and at the back, because the serial code is case sensitive.
Double-click on the CoSpace auto-driving icon on your desktop. Now, choose your level and map, which is also known as our virtual environment. We will use CoSpace auto-driving first steps as an example for illustration here. Frame rate, it is also called FPS, is a very important parameter. It will affect the robot performance if it is too low. You can check the frame rate on the status bar. It is highly recommended to keep the frame rate greater than 15 for robot smooth performance. If the frame rate is less than 15, you should change the display resolution to 1366x768. After changing the resolution, monitor the frame rate again. If the frame rate is still less than 15, you can change the rendering quality to low. The frame rate should be greater than 15 finally. To adjust the virtual environment, first, click anywhere in the virtual environment, and then, press the Q, W, E, A, S, D keys to adjust the 3D view. If you press Shift together with the keys, it will make the movement faster. If you mess up the environment, you need to click on the control panel and then click on Ctrl+H together to reset the virtual environment to the home position. To manually control the virtual robot, first, click anywhere on the control panel, and then, press the 4 arrow keys to move the virtual robot manually. As you know, there are IR sensors, ultrasonic sensors, RGB sensors and gyroscopes are installed on both real and virtual robot. While the robot is moving, the live sensor data will be shown on the control panel. Double-click on the CoSpace auto-driving icon on your desktop. Now, choose your level and map, which is also known as our virtual environment. We will use CoSpace auto-driving first steps as an example for illustration here. Double-click on the AI button to enter the programming interface. First of all, you will need to create a new project. Click on the New Project button. Please remember to give this program a team ID, a team name, a project name. Remember, once team ID and team name are confirmed, they cannot be changed anymore. However, you can change the project name if you wish. Based on the analysis earlier, we now need to convert the logic into code which the robot can execute. The first statement should tell the robot that when L1 senses the white line, the robot needs to move forward. Step 1. Let's create a statement named L1 senses white line. Step 2. After the statement name is defined, we will add conditions to this statement. We click on L1 until it turns white in color. This means L1 will sense for the white line. Step 3. We should tell the robot what to do when the condition is met. In this scenario, the robot should move forward. That means both wheels should have the same speed. Step 4. Finally, click on Preview button to see whether you have set the correct wheel speed. Great! We have completed our first statement. Repeat the 4 steps above to complete statements 2 to 6. Statement 2. When R1 senses the white line, robot moves forward. This is similar to Statement 1. Make sure we have set the same speed for both wheels. Statement 3. When L2 senses the white line, robot turns left slightly. This time, we will set different speeds to the left and right wheels. As the robot turns slightly, the speed difference should be small. Same concept applies to Statement 4. This time, the robot turns right slightly. Statement 5. When L3 senses the white line, this means that the robot is almost off track, so the robot needs to turn left quickly. This time, we can set the left motor speed to be negative and keep the right motor speed positive. Same concept applies to Statement 6. This time, the robot should turn right quickly. After we have completed our program, we should do a quick check that the logic is correct and make sure every statement has conditions and actions. Once you have completed programming, it is very important to save and build. Save means to save the most recent program that you have just completed. Build means to check syntax errors, create a C code and a dynamic data link file with extension DLL. Now you can click on the preview button to see how the robot will behave. If you wish to modify the program, click on the Stop button and you will go back to the AI panel to modify the program. Now, you can load the program which has been compiled as a DLL file using the Load button in the control panel. After successful loading, we can use the play, pause and stop buttons to control the robot's movement. We can monitor the robot's performance in the control panel. We can monitor the robot's movement from different perspectives. You can select different viewing camera from the menu bar. Choosing main camera will let you to have the global view or bird's eye view of the environment. Choosing CS-Bot front camera will let you to have a first-person view or driver's view. Choosing CS-Bot following camera will let you to have a helicopter tracking view. You can also to have the global view and first-person view in separate windows. Changing position and size settings will change the separate window attributes. Well done. In the CoSpace Autodriving Advanced level, the system allows users to add self-defined variables. For example, we need to add a new variable called CoSpace. First of all, click on VAR button in the AI panel. Secondly, give a name to the new variable. Then, set the initial value. Finally, click on Add New Variable button. The new variable is now added. It can be used in your program. You can also remove an existing variable. The CoSpace Autodriving Advanced level allows you to use advanced conditions and advanced actions to enter less complex codes using C code convention. Let's take the line tracking program as an example for illustration. Open my first program in the AI panel. Now, let's remove the IR sensor settings from the graphical section and put it as C statements in the advanced condition. Trial run and monitor the robot performance. Again, let's remove the wheel speed settings from the graphical section and put it as C statements in the advanced action. Trial run and monitor the robot performance. We can see that the robot performance remains unchanged. Let's look at the line tracking logic again. We can use if-else statements to control the program flow. Now we can put this set of statements in the advanced action. Trial run and monitor the robot performance. Apart from the if-else statements, we can also use switch case statements to express the same logic. Before we start coding, we need to define a new variable called action. Let's write the line tracking program using switch case statements in the advanced action. Trial run and monitor the robot performance. Printf is a predefined function in C. By using this function, we can print data or user-defined messages on consoles or monitors. Let's see how to add the printf statement in our code. Open my first program again. Let's change the LED status for the statement 3 to 6 so we can monitor the change of LED status later. If we want to display both wheel speed and the LED status on our console, we need to add printf for each statement using advanced action. Trial run and monitor the robot performance. CoSpace Autodriving allows you to program the robot in Python. In the advanced level, a Python template will be provided. You can use the template to write your own program. Create a new project. Click on Python icon. A template will be created. The Python template consists of variable definitions, system functions and AI function which allows user to enter their own code. You can write your code in the AI loop function. After your code is completed, save the file. The Python file will have an extension of py. Load my first python.py in the control panel. Run the program. If you want to have more example on how to code CoSpaceRobot in Python, please visit RCAP Academy YouTube channel. In CoSpace Autodriving Advanced Level, the system can convert your graphical programming in C automatically. Let's open my first program. Build to generate C code. Click on C icon to view the auto-generated C code. You can also modify or write your own code in C. Again, let's open my first program. Open the auto-generated C code file. Modify the C code. We make the LED flashing all the time when the robot tracks the white line. To do so, we need to change the LED status from 0 to 1. 0 means LED off. 1 means LED flashing. Save your code as 𝐵𝒐.c. Now let's upload the C code. Click on the upload icon. Select the virtual robot option. Select the C code file you wish to upload. After successful uploading, the corresponding DLL file will be created. Back to Control Panel, load the DLL file. Run. You will see the LED is now flashing while running. In Task 1, you need to program the robot to travel on the speedway. During its journey, the robot must stop at each waypoint for 2 seconds with LED flashing, and then move away autonomously. On the speedway, there are purple-colored patches on the floor. We can use the RGB color sensor mounted on the virtual robot to detect the color of the floor. The RGB sensor is mounted at the front right corner of the robot, facing downwards. The RGB sensor detects colors. It outputs the exact color it detects, in terms of the red, green and blue light intensities. Each channel value can range from 0 to 255. Move the robot manually. Let the RGB color sensor sense the color patch. The RGB sensor gives 3 readings for each color detected. They are the corresponding red channel reading, green channel reading, and blue channel reading. Just like programming other sensors, you need to specify the range of all 3 channels of the RGB sensor values as the condition, then set the action to be taken when the condition is met. How can we program the robot to stop at the waypoint for 2 seconds and move away autonomously? We can use duration. The duration is a countdown timer. One duration is 25 milliseconds. So 2 seconds is equal to 80 durations. 2.5 seconds is equal to 100 durations. The basic idea is to program the robot to enter a 100 duration cycle when it senses a purple-colored patch using the RGB color sensor. That's 2.5 seconds. The robot will stop for the first 80 durations, or 2 seconds. The robot will move forward for the rest of the 20 durations, or 0.5 seconds. Here is the code in GUI. When the robot senses the purple color, both wheels will be set to 0 for 100 durations. The robot moves away with both wheels' speed set to +30 for the last 20 durations. This speed setting is to ensure that the robot can move out of the purple area within 0.5 seconds. In CoSpace Autodriving Advanced level, there is a gyroscope to sense the robot's orientation. The gyroscope is mounted on the virtual robot. It senses the robot's orientation. The gyroscope comprises of the tilt sensor and compass sensor. There are 2 variables associated with the gyroscope. The rotation x gives the degree of inclination. The range of rotation x is from -90 degrees to +90 degrees. Rotation z gives the direction. The range of rotation z is from 0 degrees to 360 degrees. Just like programming other sensors, you need to specify the range of rotation x or rotation z in the condition setting, then set the action to be taken when the condition is met. For better performance, you can let the robot have different speed when it moves up and down the ramp. Please program your robot to complete the task. The sample code can be found in PPT slides. Well done. Let's work on Task 2. In Task 2, you need to program the robot to travel in a smart city. During its journey, the robot must stop at each waypoint for 2 seconds with LED flashing, and then move away autonomously. Let's analyze the map carefully. First, the robot needs to make a U-turn at the first waypoint. It will move forward at all other waypoints. Secondly, the robot needs to make a 90-degree turn when it senses pink, if the robot is on the left-hand side of the field. The robot needs to move forward for a certain period of time when it senses pink, if the robot is on the right-hand side of the field, to avoid the zigzag road. Thirdly, the robot needs to make a U-turn when it senses cyan. Therefore, we need to define 3 variables, after first station, RHS, and U-turn on cyan. During the journey, the robot needs to make correct decisions based on the information received. The robot also needs to make a 90-degree turn to avoid walls. An ultrasonic sensor is mounted at the front of the robot which can provide the robot with distance information. The ultrasonic sensor is mounted at the front of the robot. It senses the front obstacles and provides feedback in cm. When the robot moves forward, we can monitor the live feedback data on the control panel. To program the ultrasonic sensor, you have to specify the range of distance as a condition, then set the robot action to be taken when the condition is met. How can we make a proper 90-degree turn? We can use the compass sensor, similar to the earlier example. When the robot is close to the wall, it has to make a 90-degree turn. We will let the robot enter a 120 duration cycle as an example. The robot will keep turning until it has turned for 90 ± 2 degrees. We will then end the 120 duration cycle by setting the duration to 0. The robot will move on to its next action. Here is the code in GUI when the robot is close to the wall. Both wheels will be set to +10 and -10 respectively for 120 durations. The robot will keep turning until it has turned for 90 ± 2 degrees. The duration will then be set to 0, the 120 duration cycle ends. We use the modulo operator here. Please program your robot to complete the task. The sample code can be found in PPT slides. Well done. Let's work on task 3. In task 3, you need to program the robot to travel in the eco garden. During its journey, the robot must stop at each waypoint for 2 seconds with LED flashing, and then move away autonomously. You can take challenge 2 as reference, analyze the map and complete the code. The sample code can be found in PPT slides. Well done. You have completed all challenges. Let's move on to the CoSpace Autonomous Driving Online Challenge. Let's work on the CoSpace Online Challenge, or as we call it, the 𝐵𝒄𝒄 Challenge. Double-click on the CoSpace Auto Driving icon on your desktop. First of all, you need to select the correct level. Then select 𝐵𝒄𝒄 Challenge tab. Choose the challenge map you will be working on. Analyze the map and complete the code. We will use CoSpace Auto Driving First Steps as an example for illustration here. Save and build. Load the DLL from the control panel. Click on the Start button and monitor the robot's performance. When the robot reaches the finish line or when you click on the Stop button, an ICS file will be created. Save the ICS file and send it to the event organizer. Congratulations! Well done!
RCAP CoSpace Autonomous Driving Challenge Rules, U19 category. This category is for students aged 19 and below. Welcome to the RoboCup Asia-Pacific RCAP CoSpace Challenge. Automation of routine tasks is currently a concept that interests many industries. Among the most revolutionary parts of it are autonomous vehicles. These are visions of the future of city infrastructure. The main ideas they all share are self-driving cars and shared mobility. Those are set to revolutionize the ways we navigate through cities. In CoSpace Challenge, teams are required to build a real robot, develop and program appropriate strategies for both real and virtual autonomous robots to navigate through both real and virtual worlds. In the CoSpace Autonomous Driving Challenge, students are required to plan an optimum path, code both real and virtual robots to navigate in a smart city. The autonomous car needs to pass multiple waypoints before reaching its final destination. In this smart city, there are roads, buildings, color markers, black and white lines, ramp or bridges, apron tags, and waypoints. In the iCool challenge, there will only be a virtual robot. The robot has an IR sensor array, an ultrasonic sensor, a RGB color sensor, and a gyroscope. Students need to utilize the elements in the smart city to plan the best path and program the robot accordingly. Let's take a look at the game process. The duration of the game is 8 minutes. That means the robot has to complete the whole journey within 8 minutes. At the beginning of the game, the virtual robot is placed at the start station. When it travels towards the finish line or end station, the robot must pass all waypoints in any sequence. It must stop at each waypoint for 2 seconds with LED flashing, and then move away from the station autonomously. The game ends when the virtual robot arrives at the finish line in the virtual world. If the virtual robot passes all waypoints and reaches the finish line, the team rank is determined by the race time at the finish line in the virtual world. If the virtual robot is not able to pass all waypoints, regardless whether it reaches the finish line or not, the race time for the virtual robot to reach the last waypoint will be recorded. The team rank will be determined based on the number of waypoints passed, followed by the race time.
The detailed rules can be found in RoboCup Asia-Pacific official website. RCAP Academy is an outreach initiative of the RoboCup Asia-Pacific RCAP Confederation. It aims to strengthen the RoboCup spirit with continuous outreach efforts through promoting robotics and AI to the general public. On RCAP Academy YouTube channel, there are plenty of videos on CoSpace Grand Prix, which is former auto driving, CoSpace Rescue and other RoboCup categories. It includes step-by-step guidance on CoSpace auto driving and CoSpace Rescue, teams sharing, highlighted games, tips and tricks, etc. They are ready for you to explore. After finishing CoSpace auto driving U19, why not try CoSpace Rescue? In CoSpace Rescue, teams are required to program appropriate strategies for their autonomous robots to navigate through an arena, collect objects, and avoid obstacles and traps, while they compete with another team's robot that is also searching and collecting objects in the same arena.